Welcome back. We can start learning the topic attribute closure and its significance. So first is about the attribute closure definition. Attribute closure of a given set of attribute is a set of attribute which can be functionally determined from the given set. That means you are given with a set of attribute and asked to find out the closure set of given set. What we want to do? We want to identify all the attribute of the relation that can be functionally derived from the given set. So the resultant set form the attribute closure. So here we have the step to find out the attribute closure simply. So in order to find the attribute closure of a given set, we need to follow these steps. They are: first, add the elements of the attribute set to the closure set. This closure set become the final resultant set. So you are provided with a set of attribute and asked to find the closure set of the given set. So the first step is to add all the elements of the given set to the resultant closure set. So the second step, recursively add elements to the closure set which can be functionally determined from the present elements of the closure set. Okay, so consider the different elements present in the closure set and recursively add different attributes to that closure set that are functionally derived from the present elements of the closure set. Okay, so the representation of this attribute closure is like this. Attribute with a plus symbol at the right top corner. This is the representation of closure set. Okay, so consider one example. So this step become easy now. So you are given with the relation R and A, B, C, D, E are its attributes. And you are also provided with certain functional dependencies. That are the valid functional dependencies of this given relation R. What are they? AB derives C and D, D derives E, A derives C, B derives D. Okay, now we can calculate or derive various attribute closure. So first we can find out the attribute closure or the closure set of attribute A. So that can be represented as this A plus symbol. So based on our previous step, what was the first statement here? Add elements of the attribute set to the closure set. So here we want to find out the attribute closure of A, the closure set of attribute A. So first step is add A itself to this closure set. So now A is present here in this closure set. So with the current element A, consider this given functional dependency. Using this A, we can derive anything directly. Yeah, this A implies C indicates that if we know the value of attribute A, we can derive the value of C. So from this particular functional dependency, this C also added here in this closure set of A. Right. Now here in this closure set we have A and C. Now consider if this A can derive anything else with the help of this given functional dependency. No, A alone can derive anything further. And similarly check with the C also. C alone can derive anything here. And again consider the combination AC. AC can derive anything. So these two elements, we can stop here and the closure set of A contain A and C. Now we can consider the closure set of B. right? So the first step is add B to the resultant closure set directly. That means B present here. After that, with the current elements of this closure set, analyze this given functional dependency. Using this B, we can derive any other attribute. Using this B alone, with the help of this functional dependency, it is clear that we can derive the D attribute value. So we can also add D in this closure set. Now here in this closure set, we have two attributes, B and D. So now check if B alone can derive anything else. No, from this functional dependencies, here B alone can derive anything else. So check with D. Here D alone can derive E. So this E must be included in the set. Now consider the various combination of these three attributes. We need to check BD, DE, BE and BDE. Is this BD can derive anything? No. Is this DE can derive anything? No. Is this BE can derive anything? No. Again, BDE combination can derive anything? No. So here we can stop. And the closure set of B contains the elements B, D and E. Right. Now consider closure of C. So directly add this C to the resultant closure set first. So currently the closure set contained attribute C. So with the help of this C, analyze the given functional dependency. Using this C, we can derive anything else? No. With this C alone, we can't derive anything. So the closure set of C contains C only. We can stop here. Okay. Now about the closure of D. Okay. So directly D can be added to this closure set. So now D is present in the resultant closure set. Now check the functional dependency. Using this D alone, anything can be derived? Yes. If we know the value of D, we can derive the value of E attribute. Okay, so E can be directly added here. So now consider E. If we know the value of E, we can derive anything else? No. Here we have any functional dependency that is deriving by E here. So now we can consider the next combination DE. Again, DE can't derive anything. Okay, so this form the closure set of D. Again, consider the closure of E. So directly add this E to this set. Then E is present in this resultant closure set now. So with the help of this E, we can check whether this E can derive anything. No. Using E alone, we can derive anything here. So this closure set of E contains E alone. Okay, so this is the principle of deriving closure set of a given attribute. Actually, here we have considered the attribute closure of a set that contain single attribute. A single set contain A attribute, a single set contain B attribute, C attribute, D attribute, E attribute, etc. We can also find out the attribute closure of a given set that contain more than one attribute like this. Here the given set contains two attributes. What are they? A and B. Okay. So in order to find out the closure set of this AB set, directly add this attribute to our resultant closure set first. So A and B are added here. Okay. Now check. Here now we have this A and B. Using this A and B from this first functional dependency, it is clear that if we know A and B, we can identify the value of attribute C and D directly. So we can include C and D with the help of this particular dependency. Okay, now this A, B, C, D are available here. Okay, and again this, if we know the value of d is available here, so if we know the value of d, we can derive the value of e also. So with the help of this dependency, we can add this e to this closure set. Now check, if uh, using this attribute set AB, it is clear that we can derive all the attribute values of the given relation R. Is it correct? Because R is with how many attributes? These attributes A, B, C, D, E. So this closure set of AB contains all the attribute. What's the meaning? If we are given with A and B attribute values, A and B attribute values, we can derive the values of all other attributes of the given relation. That is the meaning of this closure set. If we are given with the values of this A and B attribute of a particular entity, then using that attribute value, we can derive all other attribute values of the relation R with the help of this functional dependency. That is the meaning of this closure set. Okay, now consider another example, a relation employee, and the attributes are EID, ENAME, ECT, EState. Okay, and the functional dependency is like this. EID derives ENAME, EID derives ECT, ECT derives EState. We know the city, we can identify the state in which that city present. Okay, so now consider the closure of EID. The closure set of EID contain first EID itself. EID can derive ENAME, EID can derive ECT. Okay, next, if we know this ECT, from that we get the EState value also. So we need to include this EState also here in this closure set. So this particular property of identifying our closure set, here we considered actually the transitive dependency. Is it right? Check. If we know EID, we can derive ENAME directly and ECT directly. Okay, if we know the EID value, we will get ECT value directly. And from that city value, we can derive the state information. That means EID related to ECT and that ECT related to EState. That means if we know EID, we get EState value. That is our transitive dependency. Okay, that is derived here. Okay, next is ECT, closure of ECT. So the closure set contain ECT. Then if we know ECT, with the help of that ECT value, we can derive the state information also. So EState also included in this closure set. Okay. Again, what is the significance of this attribute closure? That means, what is the significance of finding this attribute closure? With the help of this attribute closure, we can identify this super keys, basically the candidate keys of a given relation. Okay, with the help of this attribute closure, we can identify the candidate keys, all possible candidate keys of a given relation. What is this candidate key? Candidate key means minimal super key that can derive all the attribute values uniquely in a given relation. Candidate key means minimal super key. What is this minimal super key? Suppose you are given with a set of attributes. Okay, set of attributes of a given relation. Using that set, you can derive or you can identify uniquely all the entities of that given relation. Okay. So such sets of attributes form super key. Super keys of a given relation. You are given with a set of attributes, and using that set of attributes, you can identify uniquely each and every entities of your given relation. Then that set of attributes form a super key. And suppose your relation having many such super keys, many such attribute set. Using that attribute sets, we can uniquely identify each and every records of your given relation. So all such sets form different super keys. Among them, certain sets, consider certain sets, and while removing certain attribute from the set, that particular set further can't identify or uniquely identify different entities of your set. Such set form the candidate key. In a super key, while removing a single attribute or a set of attribute, that remaining set can't further uniquely identify different entities of your given relation, then such set form the candidate key. Candidate key means minimal super key. We can't remove any attribute from the given super key. Then it loses its super key property. While removing certain attribute from the super key set, then it loses its super key property. So such set of attribute is known as the candidate key. So this candidate key can be called as minimal super key. Okay. So this attribute closure is used for identifying all the possible candidate keys of your given relation with the help of given functional dependencies. Okay, so consider certain steps. The steps are used to identify various candidate keys of a given relation with the help of given functional dependencies. The first step, identify the attributes that are not present in right hand side of the functional dependencies. Identify the attributes of your relation that are not present in right hand side of the given functional dependencies. If there exists some attribute like that, that means some attributes are not present in right hand side of your given functional dependency, follow the step that specified in step 2. What is it? Find out the attribute closure of set of such attributes. That is, find out in our previous step. That means find out the attribute closure of set of attributes. The set of attribute means the set of attribute derived in step 1. What is it? The attribute set which is not present in the right hand side of our given functional dependencies. If there exists such set of attributes, then find out the closure set of attributes, such attributes. So for finding the closure set of such attributes, starting from the minimal set, then gradually grow its size. The step become clear with the help of some example. Okay, and candidate's key will be those set whose attribute closure include all the attributes of our relation. So this is actually the definition of our candidate keys. So after find out the closure set of different such attribute set, check whether this particular closure set of a particular attribute contains all the attributes of our given relation. If such closure exists, then that particular attribute set form a candidate key. If the closure set contains all the attributes of our relation, then such attribute set form a candidate key. Okay, then next is the step 4. That means in the right hand side of our given functional dependencies, all the attributes of our relations are present. Then go to step 4. In step 4, what we want to do? We want to consider various combinations of all the attribute set. Right? Various combinations, all possible combination of our attribute sets. Then find out the closure set of each and every such sets. And check whether they form candidate key or not. How to check? Or check whether that set form the candidate key, move to step 3. That means if the closure set of an attribute pair or an attribute set contain all the attributes of our relation, then that particular attribute set form the candidate key. Okay, so this is the step for finding or identifying all the possible candidate keys of a relation. Okay, so this procedure becomes simple while considering some examples. Okay, consider this relation. Relation R with attributes A, B, C, D, E. And the functional dependencies are given like A, B derives C, B derives D, C derives E, D derives A. Okay, so first follow our first step, that is whether any identify the attribute which is not present in the RHS part of this given functional dependencies. Here A is present, E is present, D is present, C is present in the RHS part of given functional dependency. From this it is clear that B is absent here in the RHS part. That means B must come in our candidate key. Many number of candidate keys may be possible for this relation R, but all such candidate keys must contain one attribute B. Okay, so identify the one or two or many number of attribute which is not present in RHS part of our given functional dependency first. If there exists any such attribute, from this it is clear that that particular attribute must come in all the candidate keys. Okay, here there exists one such attribute, that is B, which is not present in RHS part of our given functional dependency. So start from the minimal set. That is, find out the closure of B first. Minimal set means the set contains B alone. Okay, so find out the closure of B first. So directly add this B here. Then from this B, if we know B, we can derive D. So add this D to this closure set. If we know D, we can derive A. Okay, now with the help of this A and B, A is available in this closure set now, B also available here in this closure set. So using this A and B, now we can derive C. C also added here. If we know C, we can get E. Okay, so now it is clear that with the help of B, we can derive all the attribute values of our given relation R. That means if we know the value, we can derive all other attribute values of our given relation. So B is a candidate key. And is it minimal key? Exactly, it is a minimal key, or it is a candidate key. Why? By removing this B from this set, here exists anything else. So we can't identify any of its attribute values further. So this is a minimal set. So this particular B form a candidate key. Now check some other set that contains two attribute. One is B, AB. Is it a candidate key? Is there any chance to become this AB set as a candidate key? No. Why? Because while removing this A from this set AB, while removing this A, B alone can derive all the attribute values of our relation R. Because we have already derived this closure set of B. From this it is clear that by knowing the value of B alone, we can identify all the attribute values of a given entity uniquely. So, while considering this particular set containing A and B, while removing this A, with the help of this B alone, we can identify all other attribute values. So this set A and B never form a candidate key, but it form a super key. Right? Super key is never a minimal key. Okay. Again, all other attribute combination that contains B can also uniquely identify all the attribute values of our relation R. While removing this C, B alone can identify all the attribute values of a given entity uniquely. And by removing this D from this set BD, while removing the value of this D, we can identify all the values of our given relation or all the entities uniquely. And for other set also. So all such set, attribute set that contain B form super key. Okay, but this B alone can derive all attribute values uniquely for different entities of our relation R. So this B form a candidate key. This is the only one candidate key here. All other combination of attributes that contains B form super key only. Okay, consider another example. Here relation is R with the same set of attribute A, B, C, D, E. And the functional dependencies like A derives B, AB derives C, BC derives E, BD derives E. First, analyze the RHS part. Anything is absent here, B is present, C is present, E is present, again E is present in the RHS part. And A and D attribute of our relation R is absent in the RHS part. Okay, so A and D is not in RHS. So it is clear that all the candidate keys, all the possible candidate keys of this given relation R must contains the attribute A and D. Because any other functional dependencies given here, it can't derive uniquely the values of A and D attributes. So all the candidate keys, all the possible candidate keys of our relation R, it must contain attributes A and D. So start with the minimal set. That means consider the closure of A, D alone first. So directly add this A and D to the closure set. So from this given dependencies, if we know the value A, we can derive B. Now A and B is available. Using this A and B, we can derive C. And now B and D. B and D, we can derive E, or consider this one. BC, we can derive E. Any of these. Consider this one or this one. BC is available, BD is available. Consider this one or this one. From this, we can derive E also. Now check. A, B, C, D, E. All the attributes of our relation R is derived or present here in this closure set of AD. That means AD itself form the candidate key of our given relation. No need to continue further. AD itself form the candidate key. By removing any one attribute from this, that means by removing A, D alone can't identify all these attributes. Similarly, while removing this D attribute from this set, A alone can't identify all the attribute values of this given relation. So, this is the minimal set that contains two attributes A and D. this can be, and this is a candidate key. Using this we can identify all the attribute values uniquely. Okay, AD itself form the candidate key here. Okay, now consider another example. R, A, B, C, D is the same set of attributes and given dependencies. Okay, check for the attribute which is not present in RHS part. C is present, D is present, A is present, again D is present, E is present. But B is absent in the RHS part of given dependencies. Okay, so from this it is clear that in all possible candidate keys of this relation R, one of the attribute must be B. B is not in the RHS, so B must be present in all the candidate keys. All the possible candidate keys of this given relation R, one of the attribute must be B. Okay, so start from the minimal set. That means find the closure of B itself. B itself contain B first. And using this B, we can derive any other attribute value. Using this B alone, from this set of attributes, we can't derive anything else. Using this B alone, we can't derive anything else. Using this B and C, we can derive D and E. But in this closure set, now it is B only. C is not present. So the closure set of B is B only. That means B alone can't derive all the attributes of R. Find out the closure of other larger set that contains B. That means here in the RHS part, B is not present. From this we can conclude that all possible candidate keys of the given relation must contain one attribute, that is B. So first check the closure of B alone. Here the closure contains B alone. That means we can't derive all the attribute values. Okay, so consider the next higher set. That means set contains two elements, and in that two elements one must be B. So what are the possibilities? These are the possibility: AB, BC, BD, BE. One of them must be B. Okay, so find the closure of AB. AB is directly added. From this we can derive C and D. Then D is already available, so we don't want to consider this further. Then from this BC we can derive D and E. D already available here, so add this E also to this set. That means using this AB we can derive all the attributes values of our relation R uniquely. So this minimal set AB form a candidate key of our relation R. Okay, this is the minimal key. Again, consider the closure of BC. There may be more than one candidate keys for a given relation. Okay, so we need to check for other attribute sets also. So in this set BC, this is a candidate key. Next BC, directly add BC. Next with this B and C, we can derive D and E. If we know D, we can derive A also. Now it contains A, B, C, D, E, all the attributes of our relation. That means this minimal set BC also a candidate key for this relation. Again check this BD. Okay, then this BD, the closure set contain BD first. Then if we know D, we can derive A. Then this AB, it can derive C also. Then from this BC, it can derive D and E. D also already available here, so add this E to this set. Again, this BD, minimal set BD can derive all the attribute uniquely here. So this form a next possible candidate key for this relation R. Again check for this BE. Okay, so first add this BE. B alone can derive anything else and E alone can derive anything, and the combination set BE can't derive anything. That means this closure set of BE is BE alone. That from this it is clear that here all other attributes like A, C, D not present in this closure set. So this BE alone can derive all the attributes of our relation R. So this BE alone is not a candidate key. So we don't want to stop here. We need to consider next higher set that contain this BE. Okay. So what are they? BEA, BEC, BED. From this set, what are the combination? That means the set that contain 3 elements. Here these 3 form the minimal set that can derive all the attribute values of relation R. So A, B, C, BD form the candidate keys. But B is not a candidate key. So consider the next higher set that contain attribute BE. So the set contain 3 attribute, among them 2 elements are B and E. So what are the possibilities? BEA, BEC, BED. If we want to derive the closure set, no. In this set of attribute BEA, here we have attribute A and B. So here we have already derived that AB alone can derive all the attribute values. That means AB is a candidate key. So while removing this E from here, the AB alone can derive all the attribute values. So the set A, B, E, A is a super key only. It's not a candidate key. Again here, B, E, C. Here we have a subset that contain B and C. While removing this E, this B and C alone can derive all the attribute. That is, we have already derived here. This closure set of BC contain all the attributes of our relation R. So while removing this E, the subset BC can derive all the attribute. So the set BEC is not a candidate key, but it is a super key. Okay, again this BED. While removing this E, the subset contain B and D. We have already considered this closure set of BD. Here it derived all the attributes of our relation R. Okay, so again this set BED is not a candidate key but a super key. Using this set, we can derive all the attribute values of a given relation R. Okay, but this is not minimal. That is why it is super keys, not candidate keys. Okay. Consider another example. The same relation and 2 functional dependencies. Okay. Identify the any one attribute which is not present in the RHS A, D, E, B. Here C is not present here. Okay. So all possible candidate keys must contain one attribute C. So C is not in RHS. So start with the minimal set C closure. C alone can derive anything. Okay. So C alone is not a candidate key. So consider the next higher set. That means set contains 2 elements and one among them is C. So what are the possibilities? AC, BC, CD, CE. So find out the closure. AC closure is AC, BC closure is BC and If we know BC, we can derive ADE. And CD closure is CD. Then if we know D, we can identify B also. And with the help of this BC, we can derive A and E. And for this CE, closure set contain CE alone, because using this CE, we can derive anything else. From these two are not candidate keys. And this set BC and CD, it can derive all the attributes of our relation are uniquely. So these two form candidate keys. Okay. Is there any way to identify which set are possible for candidate keys or not? Consider that. We can reduce the length of our step. Why? Here, these four sets are possible in which two elements are present and one among them is C. So, we can directly say AC is not possible candidate key. Without deriving its closure set, we can directly say it is not possible candidate key. Why? Because for identifying such set that never be a candidate key, in order to identify such set, analyze this given functional dependency again and consider the LHS part now. All these are the set that contain two elements and one among them is C itself. Now check the LHS part. Here in this LHS part, C is present but A is not present. Okay, so in such case, A is in such set with an attribute which is not present in the LHS part, that will never be a candidate key. Okay, so we can directly discard these two sets without deriving the closure set. We can directly conclude that this set never form candidate and this set never form candidate. Why? Consider this. C is present in the LHS part, but E is not present in the LHS part. So, the set CE never form a candidate key. Consider these two. BC both are present in the LHS part. So, there is a chance that BC may be a candidate key. So, we want to derive the closure set of BC first. Then after deriving it, it is clear that here the BC can derive all other attribute values also. That means BC is a candidate key. And similarly, consider this CD. C is present in the LHS part, D also present in the LHS part. Right? That means there is a chance that CD may be a candidate key. So, we can derive the closure first. Then, from this closure set, it is clear that CD can derive all the attribute values of the given relation uniquely. So, CD again a candidate key of the given relation. But in case of AC, this particular set AC, C is present in the LHS part, but A is not present. So, the AC alone will never be a candidate key. Similarly, the set CE. C is present in the LHS part, but E is not present in the LHS part. Right? So, we don't want to derive the closure next. Without deriving the closure set, we can directly conclude CE alone can be a candidate key. But for this BC and CD, there may be candidate key. Okay, they may be candidate key. So, we need to derive the closure set first, then conclude whether it is candidate key or not. But in case of AC and CE, we don't want to derive the closure set. Without deriving the closure set, we can directly say AC alone cannot be a candidate key. CE alone cannot be a candidate key. Consider the previous example also. In this, we alone can't derive all the attribute set. So B alone is not a candidate key. So consider all other set that contain two elements and one among them is B. We don't want to derive the closure set of all these four attribute set. Why? Because consider this AB. A and B both present in the LHS part of this given dependency. Okay, anywhere in this dependency, A and B both present in the LHS part. That means there may be a chance AB may be a candidate key. So derive the closure set first, then decide whether it is a candidate key or not. And for this BC, B is present here in the LHS part, here also. And C is again present in the LHS part somewhere in the given functional dependency. From this, we can decide BC may be a candidate key. So derive the closure set, then conclude whether it is candidate key or not. If it derive all the attribute values or the closure set contain all the attributes of the relation, then we can conclude that BC is a candidate key. And for this BD also, B present in the LHS part of the given dependency and D also present here in the LHS part. So there may be a chance to form the candidate key. BD may be a candidate key. So derive the closure and conclude whether it is a candidate key or not. But in case of BE, B is present in LHS part here also, here also. But E is not present anywhere in the LHS part. So without deriving the closure set, we can say B alone cannot be a closure set. So go to the higher set that contain three elements in which two are BE. Then continue like that. Okay. So while removing or discarding such combination, we can reduce the length of our steps. Without deriving the closure set of each and every such combination, we can discard certain combination directly without deriving the closure set. Okay. Here also, without deriving the closure set of each and every such attribute set, we can directly discard certain possibilities and go for the higher set like AC. Higher set means set contain three attributes and two among them are AC and two among them are other set that contain three attributes in which two elements are C and E. Okay, the possibilities are ACB, ACD, ACE, CEA, CEB, CED. Okay, so consider this set contain three elements and two of them are A and C. Okay, in this, here exists a subset contain C and B. We have already concluded here that BC alone is a candidate key. So while removing this A from this set, CB can derive all the attribute set. So this ACB a super key and ACD. So here CD is a candidate key. So here we have a subset that contains C and D. While removing this A, CD can derive all the attributes uniquely. So ACD is a super key. And again ACE. Here exists no such subset. ACE can derive only ACE. Why? Because consider the LHS part of our given dependencies. In the dependency, left hand side contains C. A is not present in the LHS part. E is not present in the LHS part. That means this set never be a candidate key. Using this, we can't identify all the attributes uniquely. So it is never be a candidate key. without deriving the closure set, we can directly say here A and E not present in the LHS part. C alone is present in the LHS part. So this particular set never be a candidate key. Consider this one again. C, E, A. Here again, C is present in the LHS part, but E and A never present here. Anywhere in this given functional dependency, E and A is not in the LHS part. So directly say it is not a possible candidate key. We can directly discard without deriving the closure set. Okay, now check the closure set. The closure set contain ACE directly. Using this ACE, we can derive anything else from the given dependency. So it never be a candidate key. So here we have the subset BC. BC is already a candidate key in our previous step. So while removing this E, CB alone can derive all the attributes of our relation, so it is a super key. Similarly, while removing this E, CD can derive all the attributes uniquely, so this is also a super key. Okay. So next is another relation, R with ABCD with functional dependency. Now check, any one attribute is absent in the RHS part. In the RHS part, here we have A, B, C, D. All the attributes of the given relation are present in the RHS part. In that case, what we want to do? We want to consider all the possible combination of attributes. Then check whether they form the candidate key or not. That means consider various possibilities of attribute, various combination of attributes, and find out their closure and decide whether it form candidate key or not. Okay, so here A, B, C, D all are present in the RHS part of the given dependencies, right? So we can start with the minimal set. So start with A closure, B closure, C closure, D closure, right? So A closure contain A, B, C, D. Okay. B closure contain B alone. Means if we know the value of B, we can derive anything else. And with C, C can derive C and A. If we know A, we can derive B and D also. And with D, we can derive D alone. Okay, so again consider our previous assumption, that is, if this A is present in the LHS part, yes, in the given dependency A is present in the LHS part. That means there is a possibility for this A to be a candidate key. So derive the closure, then conclude whether it is a candidate key or not. Here from this closure set, it is clear that A can derive all the attribute values of our relation uniquely, because all the attributes are listed here in the closure set of A. So A is a candidate key. So before deriving the closure set of B, check whether B is present in the LHS part. No. So without deriving this closure of B, we can directly say B alone cannot be a candidate key. B alone cannot derive all the attributes of relation R. So B never be a candidate key, but A is a candidate key. Okay, and similarly this C. C is present in the LHS part. So there is a chance to be a candidate key. C may be a candidate key. So derive the closure, then decide whether it is a candidate key or not. So after deriving the closure, it is clear that all the attributes of the relation are listed here. So C is again a candidate key of this relation R. So without deriving the closure set of D, it is clear that D is not present in the LHS part. That means D alone never form a candidate key. Okay, so next we need to consider the next higher set of B and D. that never contains attributes like A and C, because A and C alone is a candidate key. A alone is a candidate key, C alone is a candidate key. So consider next higher set, that means set contain two elements, and the set must be formed with the help of B and D, other than this A and C. Okay, so the combination is the set with two attributes is B and D. The closure of this B and D is BD alone, because in the LHS part B and D is not present. So from this it is clear that without deriving the closure set, it is clear that BD alone can derive all the attributes of the relation. So BD alone is not a candidate key. So we can derive next higher set without including A and C here. Okay, we can derive the set containing three attributes in which two are B and D without including A and C. Here exists no such set. Okay, so we can stop here and conclude that for this given set R, we have two candidate keys A and C. Okay, one more example. Here, same relation. The RHS part contains A, B, C and D. That means all the attributes are present in RHS part. So, we need to consider all the possibilities. So, start from the minimal set, that is A closure, B closure, C closure, D closure. So, without deriving the closure, just analyze. In the LHS part, here we have D, C, A and B. All the attributes are present in the LHS parts also. So we need to derive the closure set of all attributes. Then only we can decide whether it is a candidate key or not. If any one attribute is missing in the LHS part of this given dependency, then without deriving the closure set of that particular attribute, we can say that attribute alone cannot be a candidate key. Okay, so here, but the case here is different. All the four attributes are present both in LHS and RHS. So we need to consider all the attribute closure. So start with the minimal set: A closure, B closure, C closure, D closure. So these are the closure set. From this it is clear that C alone form a candidate key. But this A, B and D cannot identify all the attribute values uniquely. A closure contain A only, B closure contain B only, D closure contain D and A only. Okay, so from this it is clear that C alone is a candidate key. So next consider the set contain two elements in which C never occurs. If C occurs, then that form a super key only. Never be candidate key, it will be a super key. So consider the set contains two attributes and the set must be formed using A, B and D. So what are the possibilities? A, B, B, D and A, D. Okay, so if C alone is candidate key, so we can avoid next level attribute set that contains C. If we consider C in the next level attribute set, that set form super key only, never be a candidate key. So the remaining attributes are A, B and D. So the possible attribute set that contain two elements are AB, BD and AD with these three attributes. Okay, now consider the closure. Here AB present in LHS. So we need to consider the closure first, then only we can conclude whether it is a candidate key or not. BD both present in the LHS, D present in the LHS. So we need to derive the closure first, then only we can conclude whether it is a candidate key or not. Again, D is present in the LHS, A is present in the LHS. So after deriving the closure set, we can decide or conclude whether it is a candidate key or not. So the closure of AB is ABCD. That means all the attributes present in the closure set. So that it will be a candidate key. Again, this BD, using the closure set of BD, it contains all the attributes of relation R, so it is also a candidate key. This AD, but this AD, A alone can derive anything, D alone can derive A only. Okay, so in this set, B and C are absent. So this is not a candidate key. Okay, AD alone is not a candidate key. Now consider the set contain 3 attributes and 2 among them are A and D. What are the possibilities? AD, C and AD, B. In this, here we have a subset that contains C. We have already derived here C alone is a candidate key. So while removing this A and D from this set, C alone can derive all the attributes of our given set. So this is not a candidate key, this is a super key. Again this, here in this step it is clear that the subset BD is a minimal key, this is a candidate key, it can derive all the attributes of the relation. So while removing this A from here, the subset BD can derive all the attributes of the given relation uniquely. Okay, we can derive all the attributes of the relation. So this ADB is not a candidate key, but it is a super key. So these two are super keys but not candidate keys. Okay. So all these are about the attribute closure and the usage of this attribute closure in order to identify the all possible candidate keys of given relation.